Problem tonight with the usual confusing, ambiguous instruction simplify. What does simplify mean? It means to just do whatever your teacher told you to do in class, right? Now here, simplify, if you try to multiply this out by doing the long multiplication you learn maybe in elementary or middle school, you're going to end up with a number in the billions, and you make a mistake if you did it by hand, let's be honest. So simplify here means just to write it as some base raised to some natural number power. Now the odd part about this is this 48. This looks like it might be tractable, the 7 squared, the 7 to the 4th, and 7 to the 8th. You know, but you got this constant, the strange constant 48, and then 1 at the end. So what's up with that? This is a weird problem. But notice that the 48 is kind of special because it does relate to the 7s. Now, y'all, I've just done most of the work here for you. I just recopied the original problem. And the cool thing is right here is that 7 minus 1 is the same thing as 6 times 8, right? 6 right here, 8 right here. And that, of course, is equal to this mysterious constant. And all of a sudden, we see the light. See, this is in the form a minus b times a plus b, right? A minus b times a plus b. The very well-known, perhaps the most famous algebraic identity in all of mathematics, the difference of two squares. The ab terms cancel out, and you're left with, on this very next line, a squared minus b squared, this piece right here. Okay, this would be a squared minus b squared, where b was 1. Okay? Now the rest of it's kind of neat. It falls out pretty nicely, but to me it's a miracle that this constant 48, once you see it, you go, duh. But when you first look at a problem like this, you look at 48, you're going, huh? But anyway, right here, we do the difference of two squares formula again. When you combine these two parenthetical expressions, you get 7 to the 4th minus 1, right? And now you have the difference of two squares working a power up, okay? So what is this? Well, this would be 7 to the 8th, 7 raised to the 8th power, minus 1, times 7 to the 8th power plus 1. Okay, now you kind of see why this 1's hanging around at the end. Okay, so you have 1 here. It was part of the original problem. And then, of course, if you carry out this multiplication, you end up with 7 to the 16th minus 1. But we still have this plus 1 hanging around, right? So we actually get the answer in our so-called simplified exponential form, 7 raised to the 16th power. So there you go, folks. And I think you can make up a whole class of problems that are like this. And it's based on this, again, looking at this from the very beginning, you're going, what is 48 doing there? Do they really want us to do this? I mean, I wouldn't know. I saw this type of problem before, and so I made up one with different constants. But if I just looked at this without any conception of the original problem, I would go, what in the hell is 48, you know? But this is the key step. The red step is the key step, and it relates it to the other powers of 7 and also this well-known identity. So anyway, let's write this. What do we get? 7 to the 16th? This whole thing is equal to 7 raised to the 16th power. And it is simplified. I think it's in the range of like 33 billion and so on. So unpronounceable number, basically, or it would take you about 2 minutes to pronounce it. But anyway, that's the final answer. Hope you enjoyed.